In this example, we're going to pick up where we left off at the modeling step in the previous part of the example, where we derived the state space model, the A, the B, the C, the D matrices. So I have them rewritten here in a much more compact, nicer looking form. So we have this 7x7 A matrix. We have a 7x3 B matrix because we have 3 inputs into the system. And we had our C and our D matrices. One thing that I will change as we go through this problem is I want to track X, Y, and Z in this example. And when we previously derived the output model, or the output equation, I was only tracking Z. So the C and the D matrix will change as we go into MATLAB here. But it's going to be fairly straightforward. We're just tracking the positions of the 3 masses instead of just the bottom mass. So that will change. A and B will be unchanged though. But keep in mind here, there are 3 independent inputs into the system, the 3 forces. So we're going to have a lot of options to play with as we look at the behavior of the system under varying the many different parameters we have, the different inputs, the different initial conditions. I'll begin again by defining the function that will really define the state equation, that xdot equation. So I'm naming it ODE3A here, and still I'll stick with just the 2 inputs, and I will define my masses, my damping coefficients, and my spring constants within the function itself. So for right now, I've just arbitrarily chosen some values to use here, and we can play with those and see how the system is going to be affected. I have to define now 3 inputs, F1, F2, F3. I will start them all just as 0, so no inputs into the system. And I'll assemble that U vector. I'm doing this also as an anonymous or inline function here as the column vector F1, 2, and 3, or U1, U2, U3 as we call it in the state space variable terminology. So U has to be a 3x1, it must be a column vector. Then I define my matrices as we found them before in the modeling step. So A is 7x7, depending on the K's, the M's, and the B's. And then the B matrix is 7x3 because I have 7 state variables and 3 inputs. So B is a matrix, it is not a vector. The size is important here. And it's a linear system, so I can express x dot as A times X plus B times U. And I do that here in 47 to make sure that XD is going to be, I'll mark it here, this is going to be a 7x1. Again, 7 state variables, so I have the derivatives, time derivatives of 7 state variables. So this we will modify as we explore the behavior of this system, but we have coded in here the A and the B matrices, and then how we determine x dot. So we have that state equation built into this function, just like before. So looking at the driver, this is where I'm going to make some changes to the first time we derived the model, but first, let's look at what we have here. When I call ODE45, I'm calling the state equation I defined in the other tab. And I'll look at this one over 60 seconds. We'll see, maybe that's enough time, maybe it's not. It's going to depend on what's happening in our system. And I'm going to start by having no initial conditions and then kind of riff from there and see how the system behaves. So what is different from the first time we modeled this is my C matrix, I'm going to pick out X, Y, and Z. So C now has 3 rows, 7 columns. So I have 3 observables, the 3 displacements of the masses by 7 state variables. So this is different than the original. And then my D matrix also has to scale appropriately 3 observables by 3 inputs. So D is a 3x3, but again, it's just the zeros matrix. And because it's the zeros matrix, I won't even include it here in my output equation, the y equals cx plus du. I don't have to worry about the d and the u because d is 0 for this example. But like the previous examples, I do need the cx term, but slightly modified in order to respect the dimensions that MATLAB gives out of ODE45. And then I'll plot my 3 degrees of freedom over time. So starting with this most basic case, no initial conditions, but also no forcing, we're going to see nothing interesting happens because nothing's happening. There's nothing that is going to make any of the degrees of freedom move from their equilibrium position. So let's now add some interest here. So let me give initial position on X just so we can get some motion happening in our system. Okay, so initial condition on X, we see that the other two displacements start at 0, as they should, and as things get into motion, X is starting to move, which, because all of our degrees of freedom are coupled together through springs and dampers, we see that actually the other 2 degrees of freedom start to move as well in this fairly complex pattern here of oscillations, especially on Z, as things start to get set into motion. And then as time goes forward, the energy is eventually dissipated out by the dampers, and we return to our equilibrium position. Let me run this a little bit longer, maybe 90 seconds, just so we can see everything going to 0. So by the time we got to, I don't know, 50 seconds, 60 seconds, everything is basically, all the energy we put in from that initial condition is lost, and we're back at the equilibrium. But we do have those oscillations for the first 40 or so seconds due to that initial condition. Let's just see what happens if I give a little bit more going on. So I'll give y an initial condition, the y displacement initial condition of negative 0.1. And we see in this multi-degree of freedom system that it definitely complicates the motion of what is happening. We still have z starting at 0, now x at 0.1, y initially at negative 0.1, but the energy is eventually dissipated out. So we can put in all sorts of different initial conditions and study how the system is behaving, how all of the degrees of freedom are behaving. And I'm here not tracking p. I could have also tracked the position of that node if I wanted. Okay, so that's no input and just some initial conditions. So let me go to 0 initial conditions and now play with the different inputs I could have into the system. Now we can modify some of these inputs here. So F1, F2, and F3. So right now they're all 0. Let's put just a simple sine function on F1 just to see how the system is going to behave. So I'll comment that out. So F1 is a sine function. F2 and F3 remain at 0. And let's see how the whole system is going to react. And let me just run it not quite as long so we can zoom in on interesting parts here. Okay, that's not bad. All right, so just running it for 45 seconds, I have F1 acting just on X, so everything is starting at 0, and now we see we start to have oscillations, and it takes about 30 seconds or so, it looks, to exit this transient phase. Like we saw in the previous example, we have this transient phase with these kind of more complicated oscillations. After 30 seconds, we have this repeating pattern happening. And we'll again go into more depth as we go into Unit 2 here. But we see that the frequency appears the same for all 3 of our degrees of freedom. And that's going to happen when we have just that one sinusoidal input. However, they are slightly out of phase. Their peaks are not all lined up, and their amplitudes are different. So this is exactly what's going to be expected for linear systems at what we call steady state. So after those transients have died off around 30 seconds. Let's look at just a little bit more complication. What if I also put a sine function happening on F2? So not 0, but sine, and make it a different frequency. So here I'm making it twice as rapid. And we run this. And probably have to run it a little bit longer to reach some kind of steady state. All right, for 60 seconds. Okay, so we do get a repeating pattern here, but look, it is certainly more complicated than when I just had a single sine function acting in the system. Now I have 2 sine functions, and they are at different frequencies. So we get a more complicated behavior by the time these transients die out. So this is happening again, it looks around 30 seconds, just kind of eyeballing it here, before we have this repeating pattern. And I can keep changing this. Let's see what if they're the same frequency. We're going to get less complicated behavior. And we do. So when they're in the same frequency, even if there's 2 forces, we see that we get back to this more simple behavior, this more sinusoidal, cosinusoidal looking behavior after around 30 seconds. And I could also make this negative, have them in what we call antiphase. So the peak of F1 happens at the valley of F2 and vice versa. And we see the response is definitely different, but After 30 seconds, we do have this repeating pattern happening of everything has what appears to be the same frequency, slightly out of phase, at least on Y and Z, and then X appears to be basically in anti-phase with the other two. Its peak is where the valleys are of the other two. So we have this robust model that we can be playing with. I won't get into now changing also the parameters. There's a lot of complications as we make our model more complicated. And like in this case, we have these 7 state variables, so there's going to be a lot of interaction between all of them as we adjust all of the different inputs, different parameters, initial conditions in the model to see how it's going to behave as time goes forward.